Okay. Um, I'm Dave Wyland. I go back to Big Bill Ragsdale's day and his merry band, and been messing around with Forth ever since. Got started by Dave Bengal. It's been an amazing adventure, still going on. I'm going to talk today about a project I've been working on. I call it Doit. It's a Forth for microcontrollers. A little bit of background. I started out on analog, spent a lot of time in computer architecture and applications work for semiconductor companies. And for the past few years, I've been knee-deep in robotics. And now that I'm working in NETA robotics, I'm about waist-deep. They make the XV11 vacuum available at Target. It's the real deal. It is a real robot. It has essentially a laser distance sensor on it, and it maps out and follows it up. Doggone thing really works. We use it. I've never vacuumed since. I'm usually the one that winds up doing it. Okay, now, wait a minute. Okay, overview. What is it? Okay, it's a Forth for microcontrollers. What good is it? Why is it? Turns out Forth is a good fit for microcontrollers. How does it work? This is really sort of old school Forth, but I've added transient local variables to it, my own flavor. There's a couple of other things that I'm not going to go into this time that are also cute, but I'm going to save that for next time. Why is it interesting? A couple of years ago, I finally got the answer to why is Forth so good? Why does it work? All the other explanations didn't seem to do it. I found the secret, and you're going to have to wait for it. And then a little bit about the status of the project. Okay. Microcontrollers are good machine controllers. They started out with telescopes. They're really good for robotics. Robotics is not about math. It's about physics. You're out there making your system work, and you're trying to make it work, not break. Okay, for about $3, plus or minus a buck, an MCU like either an Atmel Atmega 328 or a PIC, or take your choice, you get on the order of, say, 32 KB of flash, 2 KB of RAM, 1 KB of E² PROM. It runs at 20 MIPS, 8-bit MIPS, but jumps and everything else still the same. You get an ADC, you get 24 GPIOs, and a bunch of other junk on the chip. The nice thing about the MCU, like this one, this is kind of the, you might say, almost the smallest grade, is you can do a system on a chip, no fooling. As in, you get the language, Forth, the operating system, also Forth, and you have source files that can go in your flash. Okay, I finally decided I need to drop this in. Okay, what do you use it for? Okay, this is kind of your simple hello introductory robot made by Parallax. They put their own little stamp module on it. A module from Pololu with a 328 is essentially plug compatible, so that's what I've got shown here. Real robots are a little bit larger, but this gets you going. They've done very well. They sold 90,000 of them at $150 a piece to people that are interested in getting started in robots. Good people, they. Okay, what good is it? Value for an MCU. Okay, interesting characteristics about microcontrollers. Big flash, small RAM. Forth is good for this. Forth is also small code size, which is nice, and high performance, which if you're dealing with physics and you want to get on controllers fast, is important. Bonus, you have a nice big flash file, big enough to put your source code in general, as long as you're not getting too silly. Okay, now, one of the big things about Forth, you get the whole Forth thing on there. It is small enough so that you can understand it. If you're focused on the physics, you want to deal with that. If you're going to have software doing it, you want to understand all the software so you don't have to worry that it's the cause of the physics not working. So understanding the whole software system is cool. Okay, how does it work? What did I do? I did subroutine threaded fourth. Very conventional. I used subroutine threaded because I got lots of program space, big flash. What I added is transient local variables. They're local to each word, valid only within that word unless you cheat. Allocated at entry automatically, deallocated at exit automatically. One thing I added in is predefined names. I call them pronouns. A through H, if you need more than 8 local variables, you can get that too. I also put in transient global variables. This seems like a contradiction in terms, but if you think about global variables, they're not global absolutely. When the system shuts off, you don't necessarily remember what's in them. So they are transient at some level. They're transient at the vocabulary level. You need certain things if you're running editor, let's say. You may have extra buffers, etc. If you're not running that vocabulary, you don't need those global variables. So those are also transient. They're kind of different because they're named and they're unique to a vocabulary. Okay, why transient locals? Sometimes you need them or want them or they're helpful. Okay, the problem is elemental. If you're going to do over and swap, you're stuck. You have to have some local variables to do the 3-card Monte of moving stuff around. So it's all the way to the bottom. If you're doing some things like doubles, complex numbers, fill in the blank, you will want multiple local variables. So again, you can move stuff around to get that kernel function done. And having some local variables that are easy to use is better than doing a lot of stacked gymnastics to kind of keep things from using locals. Again, most variables are transient. If you're running a bunch of code, if you're running a vocabulary, a lot of cases you don't have permanent variables. You're dealing with stuff on the fly. If you're doing stream processing, the data comes in, you munge it, the data goes out, you don't need to remember it. And you don't need them after the root word, whatever application thing you're calling has completed, unless it's not the root word and you're passing on from there. Well, even if you're passing on, you do it on the stack. Okay, doing local variables. I set up a local stack, small local stack, and the top 2 elements of the stack are in RAM, effectively registers. Good old RAM here is here for RAM memory, and then below that is CVP, the current variables pointer. That's the base address. Now, if you're setting up local variables, they're both the same, and then you increment RAM here to allocate your variables. Okay, allocation. I have a locals 8 as a typical, but that's just so it's a one-word deal. You can have as few or as many as you want. You could allocate a buffer, locals, no problem. What does it do? It pushes the local stack. So it dupes the top of the local stack and pushes it all down one. Now, you increment RAM here by as many locals as you're going to have for this particular word. Typical 8, your mileage may differ. Then at the end, you deallocate it, which is you just pop the stack back. The current variable pointer goes up to RAM here, and the stack pops up to the current variables pointer. Okay. I wanted to have an integrated variable system rather than having something very disparate. Now I figured that on the vocabulary thing, that global variables are like locals. You still want to have an allocation pointer. You want to allocate when the vocabulary is initiated, deallocate at the end. So right now I've got it for like one additional vocabulary, so I've got a pointer in memory. There needs to be a small globals variable stack if we're going to get really intricate about this. It's like fourth variables, but they're named, and you can use these variables by any words that the called by the vocabulary root. As a result, you've got an integrated transient variable system. Okay, accessing, you access the locals by indexing from the current variable's pointer. So, for instance, if you've got C, that would be the equivalent of 4 ln, where ln is general locals variable thing. So 4 ln would point to the third local in RAM, where the number 4 is 2 bytes per word. Okay, the pronouns, 8 standard names. There's another word. There is a word called ln if you're going to have 130 local variables. I call them pronouns because everything uses them. They're used at all levels. Definition. Went through a couple cycles on this. So what I'm doing now is I've got the definition occurs between the start of the colon definition, just after colon name. You put in what look like ordinary fourth words, like variables. Variables doesn't do what original fourth does. Variables allocates a location on the local stack. It allocates the next pair of bytes, RAM allocation, and assigns the index in the call to the variable that you've just named. Now, what if you wanted to define a global variable? You need to do this at the bottom. But if you're going to do a global variable, it's the same kind of thing. You put global after it, and what global does is goes in and does surgery on the header you're generating, so that you refer to the global pointer, not to the current variable's pointer. Okay. Now, the named variables, they're defined just like fourth variables, with the difference between its global default, local default, and global if you want it. And this is kind of what it looks like. Okay, colon, new name. I've got locals 8 for A through H. And I put in one more, called it foo. Now, right now I've got end locals in there, which says, okay, I'll now do the execute compilation of putting in the appropriate stuff, and then you start with the code. And I go back and forth. Hopefully I'll be able to take end locals out and have it be automatic without being too obscure. Compilation, what you want at in the code is to generate paren locals, the locals execution. What that does is when you execute paren locals, okay, it pushes the local stack and it allocates the bytes. So you got local stack, and you're going to allocate all the bytes you needed to allocate for the local variables that were in the definition. So for instance, if you're just doing locals 8, you'll allocate 16 bytes. Increment RAM here by 16. In the previous example, we'd have another pair of bytes, so it would increment it by 18. And then the other thing is it sets a flag so that when you hit the end of the word, it sets a flag during compilation, so at the end of the word, you put in the pop ls, the deallocate at the end before you exit. Okay. Here's what's going on with the code. I've done this in straight 3 bytes per word, brute force and awkwardness, subroutine fourth. Right now, it's under 7K bytes worth of code. It's about 60 pages worth of assembly language. That leaves at least 16 to 20K bytes available for files, Go block files, if you will. Now, what are the constraints? Interesting thing. We've got 16K bytes. That's 128 bytes flash lines in the flash. you write 128 bytes at a time. You write a sector. Okay? Implications. Okay? Well, okay. I played around with doing a FAT8 and different kinds of stuff, and I finally said, okay, enough of that. Use some kind of a fourth block system. But you've only got 2 KB of RAM to start with, and you're going to use up, buffer space and things for that. So you got less than 2 KB, which is not enough to put into 1K flash buffers. So what I'm doing is I'm modifying it in place. So you bring it up, you modify it, and you write it back. A line, 128-byte line at a time. So you only need to buffer like 128 or maybe 256 bytes when you're buffering, maybe only 128. Okay. Why MCUs in fourth? Because fourth programs typically use few variables. This gets into the whole secret of fourth, which I'll get into. I found out in a recent thing when I was doing the good old 8051 for a client. I was munging along doing this big test program, and they had 4 KB of RAM, and I had, I defined a couple of temps. I figured I'd just, use stuff as I needed it. When I got done, I used one of the temps, and I didn't define any other word, not because it wasn't free or I, couldn't. I just didn't. Okay, MCUs, you got a big flash and a small RAM. So if you've got a good language that doesn't use much RAM by nature, this is a good thing. And you've got the flash for the code. Okay, now here's my mantra. The secret of fourth is the data stack. It's not a bug, it's a feature. It's the one thing where it's different. And everybody wants to say, let's kind of put it off to the side. Can't we go back to equations? No, equations are harmful, okay? You have to name all the data. It breeds names. If you're going to do A equals B plus C, you've got to find A, B, and C and allocate them. Oh, by the way, is B a constant or a variable? Oh, and is it a fixed or floating? And on into the night. So it's like the QWERTY keyboard. To some degree, we're stuck with it, but it's not really useful in a lot of cases. This is just background. I discovered it in 1980 without knowing it. I did what I thought was fourth, sort of. I did a data stack. Everything else was in assembly language, and I had assembly language for a few of the operations, like do, over, swap, drop, and whatnot, but I didn't do fourth. No interpreter, nothing else like that. But I got the speed up. I generated 24 KB of code on a Data General Nova over a 4-day weekend, rewrote the test driver, and on Tuesday morning, it was all there, it was all running. So I had my religious conversion. Okay, nicely timed. Okay, I'll wrap it up. Okay, so the data stack. Whoops, wrong button. Okay, so that's it. You eliminate the namespace. You don't have a lot of stuff to carry on. Status of the project. Okay, coded and tested. Fourth kernel. You type it in. 1, 2 plus dot, and you get 5. Did the flash read write? Is all in there. E squared read write is all in there. Local variable stack allocation and pronoun variables are all in there. I've got some cleanup to do. Getting the named variables compilation done. I've got a little bit on the globals. I need to figure out if I'm going to do a small global stack on that or not. The flash line editor. And oh, by the way, in terms of portraying fourth code, there is a natural way to do it. It's called HTML. Think about it. A fourth word refers to other words. A web page refers to other web pages. It's natural. Okay? Or another way of looking at it is as though it were a file tree. And I'm updating this on the Homebrew Robotics website. Thank you. Mike. No, I'm Dave. Here. Mike?